Hi, I'm going to go through a couple things here for Type 10, which are our sequences and series problems that we do have. And since it's 2020, we've eliminated some things. The only things that we're going to be covering are from College Board, what they call 10.2, 10.5, 10.7, 10.8, and 10.11. And so just a quick refresher, you're going to go through this, I guess, and read most of this, which we could call our COVID edition of this. Okay, so for geometric, the main crux is that if I have the sum, remember that this is the sum of an infinite geometric series, and we can do it a little bit more formal. A1 is equal to S infinity, the sum of infinite number of terms for a geometric is A1 over 1 minus R. And then so this right here is equivalent to this right here. So you got to be able to go back and forth from both of those, and we'll give you some examples on that. Then a harmonic series and P series, you need to know when those converge and when they do not. So a P series is when we have n to the P power, and it's 1 over that. So if P is greater than 1, then the P series converges. And then if P is between 0 and 1, then it diverges. Harmonic series is our favorite one to talk about, but then that's when P is equal to 1, therefore the harmonic series will diverge. Unless, of course, it's an alternating series with a harmonic, then it would converge. And so moving on with this one, alternating series converge under these two cases here. If we have each successive term gets smaller and smaller, or they never increase really in actuality in absolute value, and the limit as we go on is going to go towards 0. You have to write these conditions if you're justifying an alternating series convergence. And notice that it's only a convergence theorem, it is not a divergence theorem, because we do have some things called telescoping series which might mess with that a little bit. And then we have the ratio test. And then the ratio test is useful using factorials and exponentials. And so we converge if we take the next term divided by the now term, and we take the limit as n goes to infinity. If that's less than 1, then we know that the series does converge. If that same thing is greater than 1 or it goes off to infinity, then it will diverge. It's inconclusive if it equals 1, so then we'd have to use something else. Then the finding Taylor polynomial approximations, you have to memorize these formulas. And so we have two of them here. The first one is the general Taylor series formula, and really we're doing approximations. So we'll just find the number of terms, or they'll give it to us and we'll have to manipulate it. And then this one's the Maclaurin series because that's centered in around 0. And then you should memorize these, although this year you can probably have a cheat sheet with you that would have those, but I would definitely look at those so that they're easily recalled instead of you looking up things. Maybe just a glance to double check. That should be what it is. So this is the crux of the sequences and series stuff that will be on this year's exam because of our COVID situation. Okay, so for this first problem, what you have to do a lot of times, if I give you f of x, you might have to go find all the derivatives and to write a Taylor or Maclaurin series for that. In this case, though, if you can write it in the form of a geometric or infinite geometric, then you're in business, and then you can write it out by just finding what the R value is, etc. So when I look at this right here, the key to this is that this value right here is a 1. And if you notice here, it is not a 1. But what can I do to make that a 1? Well, I can divide every term divided by 3. So now I can read off of here some very easy things. First of all, that A1 is equal to 3, and then my R is equal to 2/3 x? No, negative 2/3 x. So this would be an alternating series that we do end up with. Okay? So my first term is the 3, and then since my ratio is negative 2/3 x, I'm going to multiply it by negative 2/3. And remember, anytime you can go ahead of me, that's fine. So if I multiply this 3 by negative 2/3 x, I'm going to get negative 2x. Why don't you pause and try the next couple? And then I'm going to multiply by 2/3 again, and I'm going to get a positive 4/3 x squared. And then minus 8/9 x cubed. Okay, so those are the first four terms that I do have. And then it does tell me, well, I want the general term as well. So this is a geometric. First term is the 3, and then my ratio is negative 2/3 x, and then I'm going to take all that and raise it to the n minus, and that's what we end up with. Now for this one, just make sure you write the first four terms, don't go beyond that, and then just write the general term, don't waste your time otherwise. And you don't have to simplify this, in fact you can't, so don't put those 3's together because one is affected by the exponent, the other one is not. Does the series, for number 2, does the series converge or diverge when x is equal to 1? Well, if x is equal to 1, that means that my ratio now is going to be negative 2/3. And if my ratio is negative 2/3, that's fine because remember the interval of convergence for a geometric has to be the absolute value of r is less than 1. And so we would justify this by saying, yes, it does converge by the GST, if they were asking that for us to explain. And then it says find the sum. Okay, so my first term would be 3, 1 plus 2/3. This overall would give me 5/3, so 3 divided by 5/3 is equal to 9/5. So that's the sum of that series that we do have. Now what about when we go over to x equal to 2? Well, if x equals 2, I'm going to plug this into here, and if I put in the 2, then I'm going to get r is equal to negative 4/3. And so this one does not converge. And why? Because the absolute value of r is greater than 1, and it's greater than or equal to. So if r is equal to 1, it will not converge as well. Now, a mistake that people might make is that they might go ahead and put this value into this equation and get a value. It does turn out a value, but it would be wrong because this series actually diverges, but you're finding the sum, which means it converges, so there's conflict there. Okay, so be careful with that. Make sure that it converges first before you do plug it into the formula. Okay, then number 3 says, okay, I want g of x. G of x turns out to be the antiderivative f of t. Notice that this lower limit is 0. If that lower limit is 0 with a polynomial, you're going to end up with just zeros because with a polynomial plug in 0, you're going to get zeros. So really all we're looking for is the antiderivative here. Now be careful with this 0 because if you're doing other functions that aren't a polynomial, then yes, cosine of 0 would give us a value e to the 0, so be careful with that. So all I'm going to do is I'm going to take this series and I'm just going to find the antiderivatives. So it's going to be 3x minus, this one would be x squared over 2, so I'm just going to get that. And then this one, if I bring the 2 down, it's going to cancel out, so it's going to be 2/3 4/9 x cubed. And then this one would be x to the 4th. The 4 and the 8 will cancel, so I'm going to be with 2/9 x to the 4th. I believe I did that right. Now, if they ask you to write the 4th degree Taylor polynomial, you're done. So this is a 4. So that's the 4th degree Taylor polynomial for f of x. And it stops here at x to the 4th, but includes all the other terms. Some people drop off these other terms, and no, 4th degree includes everything up to the 4th degree term. Now what we do with these Taylor polynomials is we estimate the original function at a certain value. Well, this is in and around 0, so 0.2 works for us. So P4 of 0.2 is equal to, and a lot of you will struggle with this, but just leave it. Plug it in and leave it. So 2/3 4/9. There you go. There's your estimate. So you might be asking, what's the difference between the series and the polynomial right now? Well, the polynomial is an estimate of f of x, and then the series goes on to infinity, and so that would be the exact function that represents that. It's the polynomial that represents that function because it goes on forever. It's the same exact thing, okay? Okay, so now number 5 says that we want to find the fourth derivative of g at 0. Now, I can go up here to the polynomial that represents it, and then I can go ahead and take successive derivatives all the way up to the fourth derivative until I break this one down far enough to give me a value. And if you notice, if I do this quite a few times, I bring out the 4, bring down the 3, bring down the 2, and then I bring down the 1, I guess, too, for the constant term. But we want to get this constant and break this one down. Well, instead of doing that, this formula has already done it for me. Here's the 4, here's the 3, here's the 2, here's the 1. So all I have to do is go right here and say, okay, this is my general form of the Taylor polynomial, in this case, the Maclaurin. And this right here is going to be the same thing as negative 2/9. So when I go ahead and solve this, all I have to say is that, oh, negative 2/9 is the same thing as the fourth order derivative divided by 4 factorial. And when I do that, all I know is that I can go ahead and solve this and say that the fourth order derivative at 0 is equal to negative 2 times 4 factorial all over my 9. Done. I won't even simplify that, won't do anything. There you are, done. Students get stuck on this, but that's all it is right there. And finding the patterns that relate this to this, and you should be good. And are there times when we have to find all the derivatives? Yes. If I give you f of x, that's not the geometric like I did up here. And so up here I started with this geometric function. If you recognize that, then you don't have to do all those derivatives. But if I give you the cosine of 3x, yes, you're going to have to find all those derivatives to write the Taylor polynomial. Okay? And so that's where you have to find all the different derivatives. Or sometimes they give it to you in funny terms, and they give you f prime. And then you just have to go ahead and find f double prime, f triple prime, so on. So that's when you have to do that. And so now what they have you do is manipulate. So we're going to manipulate our g of x. And so we want the 6th degree polynomial for this. And so to do h, we're just going to do 8x cubed times g of x. So I'm just going to take the terms that I have up here, and I'm going to multiply each one of them by x cubed. In order to get to the point that I want to get to, all I have to do is multiply up to this one. So that's all I'm going to do. And that's it. That's all I need right there. Okay? So all you have to do is multiply them, each one of those terms, and then you should be in business. Now for number 7, similar, except for it's a composition of functions. So I'm going to go ahead and take and put x cubed inside, and I want the 6th degree polynomial for that. So if I go 3 and put the x cubed inside, and then minus x cubed inside the squared term. So all I'm looking at is all my stuff up here. And then I should be done with that. Maybe this one I might want to simplify because they do ask me for the 6th degree polynomial. That might be the place where I would have to expand and not just leave it, because this isn't really telling us that this is 6th degree, even though we can look at it and see. So that's it for problem 1. Notice some different patterns, and maybe you recognize something. Hopefully you pick something up that you didn't know before. But I think that that's a nice link from the geometric on through to the Taylor series and the Taylor polynomials. So we're going to be doing Taylor polynomial estimates for this test. That's what you're going to be doing. Okay, I'm going to wrap up this problem 1 video, and then I'll make a new video for problem 2 and maybe the other problems there as well. Okay, thanks.